we're doing today is we are now reusing all those properties of exponents that we talked about last chapter with rational exponents. It means we're going to have fractional exponents here and there. All the same stuff works the same. All the properties hold true. The only thing that's going to be a little bit different is that you have to worry about how to work with fractions again. But remember, it should not be all that scary if you're adding or subtracting fractions, because what you have in front of you, a calculator. You should never have an issue about adding or subtracting fractions or multiplying fractions. The calculator will do the work for you if you forgot. You just have to know how to use the properties again. Remember, one of the tricks about using the calculator is the, was it alpha y equals, and you're able to get your fraction bars out. You can do a lot of stuff like that. So let's just walk through. I gave you guys these properties on the sheet, so you don't have to rewrite them out. I'm going to walk with you how we make sure we set them to go. Remember, if you're multiplying two numbers together to have same base with different exponents, all you have to do is add the exponents. So you have 1/2 plus 3/2 is how much? 2/2. Excuse me, 4/2. So you get 3 to the 4/2, which is 3 squared, which is 9. Excuse me. When you have power to power is when you multiply. So you have 3/2 times 2. What do you get? Yeah, you get 3, so you get 4 to the third. Okay. When you have two parts raised to the same exponent, you can distribute that exponent into each piece. And what did half power mean again? Good. What's the square root of 9 times the square root of 3? Or, excuse me, what's that square root of 9 times the square root of 2? 6. So this is basically 9 to the half times 4 to the half. Okay? Anytime you have a negative exponent, is it happy where it's sitting?
No.
No. So it's not happy in the numerator in this case, so where does it go?
Down.
Okay, so you have 1 over 25 to the half. And again, what does the half power mean? Square root. What's the square root of 25? Excuse me. Also, when you get into your division again, you're playing that game of war. Which one is larger, 5/2 or 1/2?
5/2.
5/2. So that means you would subtract them out. What's 5/2 minus 1/2? 4/2. And what is 4/2 simplified to? 2. So this becomes 6 squared, otherwise known as?
36.
I don't know why I was about to write 2. Thank you. And then lastly, same idea when you have a fraction all raised to the exact same exponent. You basically distributing that exponent to both terms, the numerator and in the denominator again. So what's 1/3 power means the same thing as cube root. Cube root of 8?
2.
Cube root of 27?
3.
So your answer is?
2/3.
Like I said, a lot of these things are going to be, we're using the exact same properties as we've had in the past. You're just using them with fractions. That's really all it works out to be. So today what we're going to be doing is we're working with all these properties with adding, subtracting, multiplying, dividing, as well as working with the nth roots of this as well. You're going to find out that when we work with the nth roots of this style of problem, it works out to be really, really, really clean. I have a nice little shortcut that works out for you, so you'll be happy to see that. All right? Let me show you some more examples. In this case here, I have the same base with different exponents, and I'm multiplying them together. What would you do to the exponents? What's that? Yeah, you get a common denominator. But if you look at that one, 1/2 and a 1/4, what do you get? 3/4. Yeah, I thought you were saying your answer was 2/4. I was getting twinkie back. So it's 5 to the 3/4. Is that really simplifiable to a value that'll work for us? Yeah, I was wondering. It's like, you know what it smells like? It smells like when you have your humidifier kick on for the first time in your house. You got that little bit of a musty smell to it. That's what it is. What it smells like. What's that? I don't. That's not going to be from outside, but it's that. whenever you have a humidifier that has it run for a while, you get the water in the lines just sits there and it goes in, it just gets that little bit of a mustiness. You know. That's what it smells like to you.
I don't smell.
Yeah, it's musty. It smells musty. Oh, well. Same thing works for when you're looking at, when I look at something like this, I have 12 to the 1/3 over 4 to the 1/3, all squared. How would you rewrite that? So you get 12 to the 2/3 over 4 to the 2/3. Excuse me. Can I simplify that further? Yeah. Notice how they have the exact same exponent. See how they have the same exact exponent? Remember if you had stuff like, whatever, get an example here. It was like 2x squared over x squared. You'd be able to simplify further. In this case here, you can still simplify the values out in front. This should work out clean. Yes, ma'am. No, because it's the nth root part. Because it's like, think of it as a variable if you want. It doesn't go away. Well, that is different properties because you're talking about variables in these exponents. That's logarithms. We'll worry about that. Oh, yeah, you could, when you have it written in, when you start in exponential form, finish in exponent form. You don't have, with rational exponents, you don't have to rewrite it as an nth root unless it tells you. That's all. The same thing here. When we look at the radicals, this is the same idea. Yeah. It'll say just if it basically the general rule is if it starts with the exponent, leave it in the exponent. If it starts with the root, leave it with the root. That's your basic principle when you see these types of problems. Another quick reminder about radicals. When you have an nth root of two things being multiplied together, you can split apart the radical. Same thing goes for with the division. I believe you have seen this before when there wasn't nth roots, when it was just plain old boring square roots. You've done this where this is how you were able to simplify radicals way back in the day. If you had just the plain old boring square root of 12, you knew that you could break that apart as the square root of 4 and the square root of 3. You just didn't realize that your value of n, in this case, was what? 2. Very good. Okay. You were doing this stuff in the past, but you just didn't realize you were doing it. What's going to change here is that your value of n is going to be a little bit different. Because you're going to, you might be finding a perfect square, you might find a perfect cube, a perfect fifth, a perfect fourth, something along those lines. And be able to simplify out that way. So we'll have a little bit of a little trickiness thrown in here, but it's not so bad. You're going to say? No. Oh. For example, if I look at the cube root of 4 times the cube root of 16, it really doesn't get me very far. I can't simplify either one of those, but since they have the same nth root, can I multiply those two numbers under the radical together? Yeah, and then you wind up with the cube root of, and then that's something you should be able to simplify out. The cube root of 64 is 4. Okay. Same thing with the division. If you look at the division one, I have the 4th root of 162 over the 4th root of 2. Now, do they both have the same nth root? Now, if they have the same nth root, can I rewrite this as that? What's 162 divided by 2? What's the 4th root of 81? Very good. Yeah, all right. In this section, you're going to see a lot of words that say assume all variables are possible, or assume all things to be positive. So, correct. Right.
For that first one, you
Yeah.
know that the square root of 16 is 4. Then you would have 3/4. So what do you automatically know the sheet to?
You can break it apart. There's a couple of ways of doing that. You could go ahead and rewrite this as the cube root of 8 times 2. And this is the cube root of 4, which becomes the cube root of 4 times the cube root of 2 times the cube root of 8, which becomes the cube root of 8 times the cube root of 8, which is 2 times 2, which is 4. There's many different ways of breaking it apart. So if you recognize that, by all means, go for it. That's not a problem. Okay? But yeah, that's just using all the different properties. There are many different ways to do it. Just like you would with a simplified radical. You can break things out that way as well. But what this reminds us to be able to do is how do you write radicals out in simplified form? Now, we all know how to simplify the square root of 12, I hope. Square root simplifying for us shouldn't be that scary of a deal. When we're looking for our perfect squares, we're more accustomed to being able to do that. We're looking to see if something's divisible by 4, 9, 16, 25, and so on and so on. What becomes a little bit trickier is when you start to look for your perfect cube. Remember, your perfect cubes are, what's the first one? 8, 27, 64, 125, blah, 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 blah. They get real big real fast, don't they? So when you start looking to simplify with perfect cubes, you're probably dealing with 8s and 27s a lot of times. You check and see if you can divide those out. Going back to square root of 12, what did that work out to be? Remember?
2.
3. Good. Now 54, the cube root of 54, what's the perfect cube that goes into that? 27 and what? 2. Good. So this breaks out to be the cube root of 27 times the cube root of 2. When you simplify that, what's your final result?
3 root 3.
Yeah, 3 cube root 2. You're doing the same stuff you've done before, just with a little bit larger numbers. You're still dividing out, looking to see what's the perfect cube. If you forget your perfect cubes, remember 8, 27, 64. Those are the first 3. After that, they usually get really, really large, and it's kind of tough to simplify out. Okay. The weirdness of all of this comes in when you have to rationalize denominators again. Okay? That's when the weirdness happens. So let me put this one on a different slide here. Do we agree that I can break this fraction apart to being the fifth root of 3 divided by the 5th root of 4? So just like you did in the past when you had square roots, you would break them apart. Do that again. Bless you. Thank you.
Multiply the 5th root of 4. Or the 5th root of 1.
In order to make that a perfect 5th root, how many more 4s do I have to multiply by?
4.
Oh, better yet. What's 2 times 2? If I wanted to make a perfect 5th root that encompasses 4, that's 2 squared, right? What's 2 to the 5th power going to be? Remember, 2 to the 5th power is 32? If I have 2 squared, how many more do I have to get to get it to the 5th? 3 of them. So what I'm doing here is a lot of times when you're rationalizing these weird denominators, is that your denominators are usually going to be in factors of 2s or 3s. What you want to do is break it down into an exponent. So this is 2 squared. And you know that you want to get this equal to 2 to the 5th at the very end, because that becomes simplified. The 5th root of 2 to the 5th would be 2. So that means in order to get it to this part at the end, you need to multiply this by 2 cubed. And if you do that to the bottom, you gotta do that to the top. What happens then, you get the fifth root of 2 to the fifth, which is 2. That's how you're able to eliminate the denominator. You have to figure out how many more of what denominator you need in order to make it a perfect fit. These things should be able to be broken down into perfect squares, so that way you can do 2 squared, 2 cubed, 3 squared, 3 cubed. Should be along those lines. It shouldn't be, like 7s that are just going to be nasty to have to multiply out so many times. If it is, we're talking it might be 7 cubed, so you might have to multiply by 49, along those lines. So again, all I had to do there was multiply the top and the bottom by the fifth root of 2 cubed, basically fifth root of 8. I wanted to create a perfect fit. So, what's 2 to the third? What's 8 times 3? 24. So I have the fifth root of 24. So this becomes fifth root of 24 over 2. And that's about as ugly as this stuff becomes. Again, what you want to look to be able to do with your denominator is you want to try and write this as an exponent. Try to write the denominator as an exponent, and then right away you know you have to add so many more to equal that value. I just have to add 3 more of them to get it equal to 5 in this case. For the top and bottom of that, multiply out. Okay? It looks weird, but it's the process. Okay? What? Adding and subtracting. This is very, very, very straightforward. Are those two the same?
Yeah.
What's 2 plus 7?
9.
Okay. And that's it. What you're doing is you can treat the weird rational exponent stuff, treat them as you would with common, what do you want to call it? Not common factors, variables. Make sure they have common terms. If they have common terms, you can add them or you can subtract them. If they're the same variable, if you treat it as a variable, it works out just the same way as you would as combining like terms. That's what I was looking to say. Combining like terms. Now, in the next one, they do not have the same roots right away, do they?
No.
But can you simplify one of them to make it look like the other? Can I break apart the cube root of 16? Sorry, it's not blown up enough for you. Can I break apart the cube root of 16? Into what? The cube root of what and what? What's the perfect cube that goes into 16? 8. So I can do the cube root of 8 times the cube root of 2 and subtract out the cube root of 2. What's the cube root of 8? 2. So this is 2, cube root of 2, minus, what's the coefficient out front of that nth root that you don't see? 1. Do they have the same nth root? What's 2 minus 1? 1. So your result would be the cube root of 2. Again, what you're doing is you're trying to break it apart into having the same common nth root. If you get the same common nth root, then you just worry about the numbers out in front of the nth roots. Add them or subtract them. It's all about being able to set it up until you have that common nth root. Remember, you're trying to simplify out. You're looking for perfect squares, perfect cubes, perfect fourths. What's fourths? 2 to the fourth is 16, 3 to the fourth is 81. After that, it's big. Yes? Oh, I thought you were asking a question. Never mind. Sorry. Put you on the spot. All right. Now let's mix this up with some variables. Where's the variables? When you have variables, when you're working with them, whether it's nth root or when it's written up as exponents, you use all the same properties. The exponent ones tend to be a little bit trickier than the nth root version of them. Also, one of the things that you recall whenever we took square roots all the time, you know how if you had an equal sign, you'd have plus minuses? Again, in these problems, they're always going to say to you, assume all variables are positive. So you don't have to worry about doing plus minus on these things. Okay? You don't have to worry about that. The instructions will say in the book, assume all variables are positive. So let's take a look at something like this. I'll move these off to the side. That's an nth root style problem. I have the cube root of 125 y to the 6th. That means I'm basically taking the cube root of both of those two terms. What's the cube root of 125? 5. Okay. Now, here's where it gets interesting. There's nothing left over with that 5, correct? It was a perfect cube. I have nothing left to put inside there. Now, when you work with variables, when it's dealing with nth roots, when it looks like this, how many times does 3 go into 6? How many are left over? There's your answer. What you're doing when you're working with nth roots and variables, you're seeing how many times does that nth root go into the exponent. However many times is how many of them come out of underneath the radical. How many are left over stays within. If this looked a little bit different, if this was the cube root of 125 y to the 8th, again, I would have just done the cube root of 125, which was 5. 3 goes into 8 how many times? Twice. Means I can take 2 out. And how many are left over inside? 2 more inside. So we get, it's a nice, handy little shortcut that works for nth roots. You're doing short division. How many times does it go in? How many are left over? What stays under? What goes up, comes out? Okay. Let's try another one with the division here. I have the 4th root of x to the 4th over y to the 8th. There's no numbers to have to worry about. So basically I'm asking, how many times does 4 go into 4? Once. Is there any left over?
No.
So one of them comes out. Oops. How many times does 4 go into 8? Any left over?
No.
2 of them come out. And you're simplifying. It's a nice little trick. It's a very nice little trick to show you guys how that stuff works. The book does it a little bit differently. Trust me, this method is a little bit cleaner. Just talking about short, quick division. Because if you wrote it out the long method by raising everything up to those exponent rules, you'd have improper fractions, and you would see that 5 over 2 is 2 1/2. So you can take 2 out and left 1 in. It's a little bit messier. That's why I just do it the shorthand, but it's a little bit quicker. All right. Let me show you what it means when you work with the exponent style method. Let's take both of these. Again, when you're working with the your exponent ones, when they're written up like this, it's not as clean. This mirrors the style that we did in the first section of 6.1, where you had to play the game of war with everything. You had to worry about your negative exponents, positive exponents, moving stuff around. This is a little bit messier, to say the least. And if you recall, every time we did one of these types of problems, the first thing I would always tell you guys to do was take care of your numbers first, then make all of your variables have positive exponents before you worry about anything. Okay? So in my first example, I have 6x y to the 1/2 divided by 2x to the 1/3 z to the negative 5. By taking care of my numbers first, what's 6 divided by 2? 3. X, y to the 1/2 is all positive variables. X to the 1/3 is a positive variable. Z is now a positive variable. I moved all my variables around to make sure they had positive exponents first. From there, I play those games of war. I have x and an x to the 1/3. Who wins?
X.
X. So what's 1 minus 1/3? 2/3. So I have nothing else to have to move around or do anything else. So my final answer would become 3x to the 2/3, y to the 1/2, z to the 5th. And that's done. When you write those out, go numbers first. Make all of your exponents positive by moving them around. Then simplify variable by variable. Don't try to do too much at once. Okay? Don't try too much at once. Excuse me. Cursor happened to step right on the middle of the problem. There. Now I have a whole bunch of junk raised to the 1/2 power. What do you think I have to do with that 1/2 power?
Square root.
I could square root it, or what else could I do? What else would I do with this power? You're doing this. What does that mean?
Square root.
Well, you could write it as a square root. I mean, if that's what you want. But what I'm saying is we're distributing that root to each term. So yeah, if you want to do a square root, it's fine. I'll show you how to work it that way. What's the nth root out in front? It's 2 now, right? Do you guys agree? What's the square root of 9? Okay. 2 goes into 2 how many times? Any left over? 1 comes out. 2 goes into 10 how many times? Any left over? 5 come out. If you want to rewrite it as an nth root when you have something like that, by all means, go ahead. Suggestion that I was going to show you guys is that you could distribute that 1/2 power by using your power rules, and you get 9 to the 1/2, u to the 2/2, and v to the 10/2, just by using the properties of exponents, which simplifies out to be the same exact thing. It works either way. If you want to use the properties of the exponent rules by writing those things out, go for it. If you want to break it down into the nth root style, by all means, it's no problem. Okay? The property of exponents are going to be better off for you when it's not an easy fraction, not the 1/2 or 1/3. If it's 2/3, if it's 3/4, you're going to want to use those properties of exponents as opposed to trying to break it down into the nth root. Because remember, the nth root stuff is going to be with 1/3, 1/2, 1/4. Okay? Let's string all of it together. Let's take a second to see if you can get these. Yeah. All right. Let's do the first one. All right. I know that the rationalizing of the stuff gets messy here. Can you take the 5th root of 5? No. There's no perfect. So what I'm going to do is I'm just going to start putting this here and leave the 5 in. I can't simplify it. How many times? Now I'm going to go to the variables. 5 goes into 5 how many times? Any left over? Take an a out. 5 goes into 9 how many times? Once. How many are left over? 5 goes into 13 how many times? How many are left over? And you're done. And you're done. What you're doing is you're trying to see how many times does that the nth root go into each of those exponents. Again, this 5 goes into here one time with no leftovers. So the a, just one a comes out. The 5 goes into the 9 twice. Or excuse me, once. I can do that. Goes in once with 4 left over.
But is it like multiplied?
Yeah. It's ABC squared times the 5th root of 5b to the 4th c cubed. Now the little bit of a nasty looking one. When this happens, you know that you're going to have to get rid of the radical in the denominator. Right off the bat, in order to make 3 go into something an even amount of times, for lack of a better term there, what would I have to turn that 7 into? Not necessarily. What's the next multiple of 3? 9, right? How many more 7s would I have to, how many more y's would I have to add to it? 2 of them. So right off the bat, I'm going to do this. And this is all a cube root here. What I'm doing is I'm going to be simplifying that denominator first. I'm creating, let me write this below here. Let's see it better. What I'm doing is I'm creating this. It's just an x, correct? What I'm doing here is I'm creating a multiple in the denominator that's divisible by my nth root. The next number that 3 goes into cleanly after 7 is 9. So when you simplify this out, there's really nothing else you can do in the numerator except rewrite it as the cube root of x, y squared. But 3 goes into 9 how many times? Are there any left over? And that's how that would look. What you're doing is you're trying to create the next available multiple of whatever your nth root is. The rationalizing of these things are going to be the trickiest of everything that we do. The rest of them, when you work out the nth roots and you're just dividing through, usually tends to work a little bit cleaner. What'd you get? But you don't want to have roots in the denominator. I see what you're saying, though. Let's say, yeah, why it's an nth root. You want to have, you don't want to have rational expressions in the denominator. You want to have, that's why. And that's kind of like the same idea of leaving the square root of 2 in the denominator. You don't want that. Because that's 2 to the half. You don't want that. Yes, sir?
When you say the nth root,
When I'm saying the nth root, it's this value here. It's,
just a 3 or is there anything?
it could be anything. It could be a square root. This one, the nth root was the 5th root. Square root would be a 2.
Any square root, or any root.
Any root, yeah. Any root. Okay. Adding and subtracting, same exact rules apply. You gotta have a common root to make it work. If you do, it's all good. In this case, you treat it as combining like terms. It means the exact same thing as you would numerically. You still simplify before you add or subtract. In that first example, it's 5 root y plus 6 root y. What would you get? 11 root y. Here you have 2xy to the 1/3 minus 7xy to the 1/3. Do you have the same variables with different coefficients here?
Yeah.
Same exponents and all that kind of stuff? What's 2 minus 7? It's -5. So you treat it the same way as you would. You've got to have those common terms in order to do the operations. What becomes weird is when you have to worry about any simplifying towards the bottom here. Again, you'd have to simplify your radicals to make them work, to see if you can get it to go. In that first part, we have 3 cube root of 5x to the 5th minus x times the cube root of 40x to this x squared. So what we want to do is try to simplify out each term. I can't take the cube root of 5, but can I take the cube root of x to the 5th? Yeah. How many times does 3 go into 5? how many are left over? So I can take out an x, and I'm left with the cube root of 5x squared. Okay? What's a perfect cube that's hiding within the 40? Here's a hint. What's 40 divided by 5? Is it on the ceiling? 8. Okay? So the cube root of 40 would be the cube root of 8 and the cube root of 5. Okay? It's helping you to create that common terms. So you break it apart. You wind up with minus 2x cube root of 5x squared. Now can I combine these two terms? So I have 3x cube root 5x squared minus 2x cube root 5x squared. What are you left with? X.
5x squared.
Yeah, x cube root 5x squared. Remember, when you're working on these style problems, what you have to make sure you get is that common root throughout. Okay? I'm giving you odd problems tonight, so you can check your work to make it go through. Oops, that did not blow up. All right? Give those a shot. See how we go with this. Tomorrow's stuff uses the same thing, but in just a little bit more of a combination style. And you'll see that you'll see how they interact here pretty quickly. Okay?
How much did we